Good day, ma'am. I'm Shane Batelier, joined with Jasmine Nueva and Ron Galvez, and this is our final project presentation. For this term, we work on two projects. The first one is a regression-based transistor count prediction using a GPU dataset, and the second is a neural network for steering prediction using sim racing telemetry. Let's begin with our first project. This project focuses on predicting the transistor count of GPUs using regression models. Our goal was to analyze how GPU specifications evolve and determine whether these patterns can be modeled accurately. GPUs have evolved extremely fast over the past few decades, mainly because of improvements in transistor density, manufacturing processes, and overall architectural design. These advancements have made GPUs faster, more efficient, and capable of handling increasingly complex workloads. Because of this rapid growth, it becomes important to look at how GPU specifications change over time and whether these trends can actually be modeled mathematically. For our study, we use a GPU dataset that covers models released from 1986 up to 2026. Using regression, classification, and clustering techniques, we examined key characteristics such as transistor count, release year, and pricing. Through this analysis, our goal is to identify patterns that can help predict future performance trends, classify GPUs into different market segments, and reveal natural groupings that appear across multiple GPU generations. For the objectives of our project, we focused on three main points. First, we wanted to analyze whether GPU transistor counts follow exponential growth similar to Moore's law. Since Moore's law suggests that transistor density doubles roughly every 2 years, we tested if this pattern is still visible in modern GPUs. Second, we aim to identify natural clusters in the dataset. By grouping GPUs based on their specifications and pricing, we could observe how different models naturally fall into categories such as budget, mid-range, or high-end. Lastly, we wanted to visualize GPU trends over time. This includes looking at changes in pricing, improvements in technology, and overall performance growth. By plotting these trends, we get a clearer picture of how GPUs have progressed across different decades.
Hello, Miss. So, for our methodology, uh, to reiterate, our project focus is to tackle Moore's Law, which states that transistor counts in integrated circuits double approximately every 2 years. So, it's not only integrated circuits but also GPUs and other computational components. Then it aims to predict future GPU transistor counts using linear regression based on previous studies. Our tools and resources that were used were MATLAB for analysis due to its powerful capabilities and developer community. The datasets was also sourced from Kaggle, containing information from the 1980s to present day, and Kaggle is a data science community sort of website. Yeah, and then the dataset we used includes key data points like transistor count, memory type, GPU name, and release date. The dataset contains thousands of rows from various GPU manufacturers like Intel, AMD, and many more from the 80s and 90s that are either bought already from others, but yeah, that require data cleaning due to some of them having missing or erroneous entries. So next is the data processing. So as stated earlier, our data is not fully complete in the dataset. So some cleaning was involved, removing incomplete or incorrect data entries to ensure analysis accuracy, and focused on key variables like the year and transistor count, since that is what we're mainly after. And lastly, just an overview. So we applied linear regression for its simplicity and ability to provide a rough estimate of future transistor counts, and the model helped make the analysis of Moore's law more accessible and perceptible. So next is our data results and analysis. So based on the figure, exponential growth pattern is shown. It follows the Moore's law, a predictive model with a red line. It's It acts as a predictor with a release year and transistor count. Then that growth trajectory trend from supposedly 2000 to 2010s, but this figure is where the regression line is included. It's more compact because super laki po kasi ng dataset, so super skewed. So you can see may parang isang outlier po sa pinakataas tapos sobrang dami sa baba. Kaya ganun po. Next is the cost function, pretty much to find the theta 0, theta 1. It's more of a curve shape, so it did do some calculations to find out which is the best theta to zero in, but yeah, as we can see, it doesn't have much in the way of valleys and hills, but it is. And lastly is the contour plot, a top-down view, pretty much a figure showing how the program slowly but surely circled in towards the agreed upon theta value. So that is denoted by x, just like in our lab activities. So yeah. And next is our clustering. Again, this due to the great what you call this, just the greatly skewing of the dataset because of several outliers. Majority of the bottom line is some would call budget tier, but $1,000 is not really budget tier. But yeah, that is just adjusted for our just for demonstration purposes. But their mid range is from $1,000 to $2,500. High end is from 2,500 to 5,000. Enthusiast is 5 to 10, and professional is 10,000 and above. Professional tiers, they have like 153 million transistors according to the dataset, and they're most likely used for AI training and running. That's why it's so expensive. But yeah, due to just the dataset being so large and including GPUs of that tier, it's very skewed po. Kaya ganun. So the figure shows GPUs from 1986 to 2025, and it's clustered based on price with 5 different levels. So thank you, Miss.
For project number 2, we built a neural network that predicts steering inputs using telemetry data from a racing sim. So instead of using images or video, our model learns driving behavior purely from numerical data. Modern racing simulators generate a lot of telemetry: wheel speeds, suspension data, acceleration, and so on. So steering is one of the most sensitive controls. So in this project, we wanted to see if a neural network can learn how a driver steers. We worked with more than 94,000 samples and over 60 input features, and the goal was to predict the steering value from -1 to +1, so from leftmost to right. So our objectives were straightforward. First, we needed to clean and prepare the telemetry dataset. Then we built a feed-forward neural network that outputs continuous steering values. After training, we evaluated the accuracy using RMSE and R squared, and we visualized how well the predicted steering matches the actual steering from the simulator. For the scope and limitations of this project, one is that this only focuses on steering prediction, and we used simulated data instead of real-world driving. Another limitation is that we didn't use temporal models, so every sample is treated independently without consideration to previous frames. But this also made the model lighter and faster to train. For the RRL, telemetry is widely used in motorsports, especially for analyzing driver behavior, and vehicle performance. And previous work in steering prediction often uses image-based models, but our approach is different because we used raw telemetry only. It's similar to behavior cloning, but using numerical data instead of video. Now, our data set, we got it from Kaggle, and it contains roughly 94,000 samples. Each row has more than 60 measurements, including wheel slip, tire data, suspension, compression, velocity, orientation, powertrain output, and driver inputs like throttle and brake. And our target value variable is the steering value, normalized between -1 and +1. So -1 is leftmost, 0 would be centered, and +1 would be rightmost. So to prepare the data, we started by loading the telemetry file and removing non-numeric columns and invalid entries. Then we extracted the steering values and rearranged the data into the MATLAB neural network format. As for splitting, we used 70% for training, 15% for validation, and 15% for testing. We also applied a fixed random seed to keep the results reproducible. As for the system architecture or the design of our model is a simple feed-forward neural network. It takes over 60 features as input and passes them through two hidden layers with 32 and 16 neurons using ReLU activation and outputs a single steering value. And we used MATLAB's Levenberg-Margot training algorithm, and all inputs were normalized to help the model converge more effectively. For the training process, we used mean squared error as the loss function. Then the network usually trains for around 100 to 150 epochs, and MATLAB's early stopping feature prevents overfitting by monitoring the validation loss. Using a fixed random seed also makes sure that our model behaves consistently each time we run it. So after training, the model achieved an RMSE of around 0.06 to 0.09, which means the average prediction error is quite small, or near zero. Our R-squared value is above 0.90, showing that the model can explain over 90% of the steering behavior in the data. Overall, our model performs very well for a simple feed-forward architecture and proves that telemetry alone is powerful enough to capture driving behavior. So here we're showing the overall performance of our neural network using three visualizations. Starting on the left, we have the prediction accuracy scatter plot. Each point represents one sample from the data set, comparing the actual steering value to our model's prediction. The red dashed line is the perfect fit line where prediction equals actual. We can see that most points fall close to that line, and the R-squared value is about 0.95, which means that the model explains around 95% of the steering behavior, which is pretty good. That's a very strong correlation for a simple feed-forward network. In the middle graph, we zoom in on the steering tracking over time. The blue line is the actual steering, and the red dashed line is the predicted steering. Even though the steering changes rapidly, especially in tight corners, the predicted line follows the actual line very closely. And this shows that the model is able to capture quick changes in driver input and not just slow or smooth steering. And finally, on the rightmost, we have the error distribution histogram. And most of the errors are clustered tightly around 0, which means that the model tends to be accurate the majority of the time. The root mean squared error value is around 17.55, even though the scale of the steering values go from about -150 to +150 here. The error remains relatively small compared to full range. And overall, these three graphs together show that our model not only aligns well statistically, but it also performs well visually and behaves consistently across the entire dataset. So we also created a simple web page to visualize our model. On the left, you see a live steering wheel that rotates based on the actual angle, while the predicted angle is shown beside it. On the right, the line chart compares the actual steering, which is in blue, with the AI's prediction over time, which is in red. And below, we have playback controls and the option to upload a CSV, so the dashboard can visualize real model outputs. And at the bottom, The key metrics are squared, RMSE, sample count, and accuracy, which summarize the model's performance. And yeah, that's our presentation. Thank you so much for listening.